Hello friends, welcome back. Today we are going to learn a new topic which is sampling of discrete time signals. So first we have learned sampling of continuous time signals in which we were converting a continuous time signal into discrete time signal. Now this is a sampling of discrete time signals. So we are sampling it to a different sampling rate. So firstly, the sampled version of the signal is taken and it is downsampled or upsampled. So we are changing the sampling rate and it is also termed as resampling. Okay, so we can increase the sampling rate or decrease the sampling rate. Okay, so there are two types. So first, let us understand why resampling is required. So we see many times that signals are present at different sampling rates. So you can record an audio signal with a sampling rate which is 8 kilohertz or 16 kilohertz, or sometimes you observe the music files which are sampled at 44.1 kilohertz. So when you are going to use these kind of different sampled signals and you want to make those system compatible, you need to make those sampling rates compatible to each other. So you want to convert one signal sampled in one sampling frequency to another sampling frequency. So that's why we require resampling to make the systems compatible to each other. So there are two types. One is downsampling and other is upsampling. So today we are going to learn downsampling. So let us learn what is downsampling. So in downsampling, we are removing some of the samples and keeping some specific samples of the signal. So let us take one example signal x of n. Say it is 1, 2, 3, 4, 5, 6, 7. This is 0th sample. So let us say y of n is a signal which is a downsampled version of x of n by a factor of 2. So let us see what happens here. We take 1 as it is downsampling by a factor of 2. Means take one sample, leave other. Take another sample, leave next sample. So it is like this 1, 3, 5, 7 and so on. If the signal exists further, let us see if some signal y of n is a different downsampled version. That is, say, let us say we downsample it by a factor of 3. So the signal becomes original signal. We take the 0th sample, then skip 2 samples. Next sample is 4, then skip 2 samples, then next sample is 7. So we are actually compressing the signal. We are throwing some of the samples of the original signal. So from the sampled version signal, you cannot get back the original signal. Okay. So it is lossy kind of conversion. Okay. So downsampling is lossy. We can say it is lossy. We cannot get all the samples back because you don't know here which samples were there, 2, 3. So by seeing this signal only, you cannot tell these samples were 2 and 3. Okay. So it is lossy. So let us draw a diagram to explain how it is done. So we have to take some steps. So it is a signal, let us say it is a sampled signal. So it has samples like this, and we want to convert this signal to some another signal, another with some different sampling frequency. We want to remove some samples. Let us say we want to take every third sample. So we will multiply the signal x of n by the signal s of n, which is a train of impulses like this. So we don't want this sample, so multiply it with 0. Again we don't want this sample, we want this sample. Okay, third sample. Then we don't want these two samples and want this third sample. Then we don't want, like, let's say it's done on both sides like this. So it is s of n which is multiplied to x of n. So what we get here, let us name it xs of n. So we are going to get the same signals, but some samples are made 0. So this sample is 0. So we are going to get this sample, which is exactly the same as this sample. Okay. So now same procedure is repeated again like this. So say it was the sample like this, but it is not the signal which we want. So it is just the sampled version which is having zeros in between. We don't want these zeros. So we want a signal y of n, which is actually a compressed version. So we are taking only the non-zero samples here. So it will be like this. Okay. So y of n is a compressed version of xs of n. So you can write an expression for this y of n. Y of n is the downsampled version of x of n by a factor m. Say, let us say this is m. Okay. So we can say y of n is equal to the compressed version of xs of n. So xs of n is xs of mn. Okay. And what is xs of n? Xs of n is a multiplication of x of n into s of m. So this signal is equal to x of n, where n is equal to 0 or plus minus m plus minus 2m and so on, and it is 0 otherwise. So what is s of n? Let us look. So this is del of n, simple unit impulse signal, and this one is the shifted version of del of n. So we can say del of n minus m. So these are the m samples. So it is del of n minus m. This is del of n minus 2m. Okay, and so on. So we can write an expression for s of n. So s of n is equal to sum of all the del of n minus 1, del of n minus 2m, and on this side del of n plus m plus 2m, like this. So this del of n minus k m, where this k is varying from minus infinity to infinity. Okay. So now let us try to see what happens in the frequency domain. So we want to draw the spectrum of the final version, that is y of e raised to j omega, and we want to see what happens to that spectrum when the signal is downsampled. Okay, so we want to check that if there exists some problem in the spectrum. Okay, or can we go simply with the downsampling with no constraint on it. Okay, so let us draw that signals. Firstly, we'll write the expressions for the spectrum. So as x of n and all these signals are in discrete time, we have to take discrete time Fourier transform of the signals. Okay, so first of all, say y of Fourier transform of y of n is y of e raised to j omega. Y of e raised to j omega. It is the Fourier transform of y of n varying from minus infinity to infinity, e raised to minus j omega n. So this is just the formula of Fourier transform, discrete time Fourier transform. We know that y of n is this, xs of mn. So just write this, xs of mn e raised to minus j omega n. So we want to write it in terms of Fourier transform of xs of e raised to j omega. Okay. So let us change this mn to something. Let us write mn is equal to p, then n is equal to p by m. Okay, so we'll change it in this step. So y of e raised to j omega, this will become here, n will change to p, and this p by m. Now n is minus infinity to infinity. We'll put this value here, minus infinity. So p is going to be the same, minus infinity to infinity. Okay. xs of p e raised to minus j omega n. Now n we are changing it to p by m. I write m here. Okay. So you can observe this equation. This is the Fourier transform of xs of p. So you can write it xs of e raised to j omega. But here omega by m is there. There is a change. So we can write omega by m like this. So now there is a new question. What is xs of e raised to j omega? Then we can write xs of e raised to j omega by m. So let us find what is xs of e raised to j omega. So we have to take transform of this. So let us take a transform of this xs of e raised to j omega. So here we can observe it is multiplication of two signals. So in the spectrum Fourier transform domain, so it is going to be a convolution of these two spectrums of x of e raised to j omega and s of e raised to j omega. So let us say we'll write this formula first. 1 upon 2 pi x of e raised to j omega convolved with s of e raised to j omega. Now we have expression for s of n. So s of e raised to j omega. I'll directly write the expression. I'll not go into the proof. We'll have a proof of this. If you say, I'll make one separate video for this. So this s of e raised to j omega is nothing but 2 pi by m. This k varying from 0 to m minus 1 del of omega minus k omega s. Okay. Now let us put this here. Okay. So in this I will write this expression e raised to j omega. So this is our main expression. We want to keep it here. And I'll rub this. So let us put s of e raised to j omega here and let us see what happens. Xs of e raised to j omega, this expression, is equal to 1 upon 2 pi x of e raised to j omega, and it is convolved with this 2 pi by m, 2 pi by m summation k varying from 0 to m minus 1, this del of omega minus k omega s. Okay. And this bracket complete here. Now we can observe this. This is equal to 1 upon 2 pi. So I'll write this 1 upon 2 pi and this 2 pi get cancelled. So I'll write directly 1 upon m. And I'll take this inside this. Say, let us see what happens. So you know the convolution property of this impulse function. When a signal is convolved with impulse function, what happens? It is getting shifted by this shift. So if we are convolving x of e raised to j omega with del of omega, so it is going to be like x of e raised to j omega only. If we are convolving x of e raised to j omega by del of omega minus 1 omega s, then this is also going to get shifted by 1 omega s. So it will become x of e raised to j omega minus 1 omega s, like this. So it is a sum of all these k's starting from 0 to m minus 1. So we can directly write it as 1 upon m. Directly write it as a sum of all, sum of k varying from 0 to m minus 1 x of e raised to j. Where is omega? I'll write omega minus k omega s. Omega minus k omega s. Okay. So this is the expression of x of e raised to j omega. Now we want y of e raised to j omega. So let us write that y of e raised to j omega. Now we'll put this value here. So what we want to do? We want to express it in terms of excess of e raised to j omega. Okay. So what is excess of e raised to j omega x? You want to take this expression, put it here. Put just where there is omega, you have to put omega by m. Divide the frequencies by m. So it will become 1 upon m, k varying from 0 to m minus 1 x excess x of e raised to j omega minus k omega s, and is divided by m, this factor. So this is going to be the expression, final expression, what we were looking for. Okay. Now, with this expression, we'll draw the spectrum and let us see what happens. So what spectrum we are actually looking for? Say if I put value of m is equal to 3, for example, so y of e raised to j omega, which is equal to 1 upon 3, and this sum of k varying from 0 to m minus 1, 3 minus 1, which is equal to 2, x of e raised to j omega minus, now value of k, here I'll put k omega s, divided by m is equal to 3. Okay. So let us expand this summation for m is equal to 3 and let us see what is the expression. I am writing this expression y of e raised to j omega in expanded form. Y of e raised to j omega is equal to 1 by 3, and in the bracket for k is equal to 0, x of e raised to j omega by 3, as this k is equal to 0. Okay. Now I am taking omega s is equal to 2 pi. As you know that originally sampled version of the signal is having its images. So these images are placed by a factor 2 pi, 4 pi, 6 pi, like this. So we'll draw this. So I'll put the value of omega s is equal to 2 pi, k 2 pi. Okay. So plus next k is equal to 1, x of e raised to j omega minus 2 pi by 3. Okay, this factor. Next, x of e raised to j omega minus 4 pi, k is equal to 2, last, and this whole bracket is multiplied by 1 by 3. So the downsampled version of the spectrum is again compressed. So we have seen this before also, that this sampled version of the signal is compressed by a factor. So I'll rub this formulas. Now we'll go for the spectrums. Let us say it is the original spectrum e raised to j, x of e raised to j omega, and I'll draw here pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. So this is the frequency. Minus pi, 2 pi, minus 3 pi, minus 4 pi, okay, and minus 5 pi here. So I'm drawing a long axis because when this factor omega by 3 happens there, so we have to spread the spectrum. Okay, so omega by 3 spreads the spectrum by a factor of 3. So first I'll select a shape like this, which is pi by 3, highest frequency. So here minus pi by 3. Okay. Now you know that a sampled signal is originally having the images. Let us say it is amplitude, its amplitude is 1. Okay. We know that it's compressed by a factor of 1 upon ts, but here I'm assuming it to be 1. So let us have its images. So images are at 2 pi, 4 pi, 6 pi, minus 2 pi, minus 4 pi, minus 6 pi, and so on. Okay. So let us draw the first. So it is 1 by 3 x of e raised to j omega by 3. So just we have to expand this signal. So 0, center will remain at the same point. This pi by 3 will go to pi by 3 into 3, that is 2 pi. We have to draw the axis exactly so as to, we need to sum these all together. So this is going to be like this, 1 by 3 factor, this is 1 by 3, and it is going to spread like this, expand like this. Now this 2 pi will go to 2 pi into 3, that is 6 pi. So this center will be like here and the signal will be like this. So this I draw here 6 pi. It will start from 5 pi to 7 pi. Okay, so this is 0, this is pi, this is minus pi. Only I will draw the reference point which we need. So now this will, minus 2 pi will go to minus 6 pi. Minus 6 pi I am not showing there. So it is like this. Now next we'll draw this part. Okay. So it is 1 by 3 x of e raised to j omega minus 2 pi by 3. Okay. Now to draw this, just we can simply omega minus 2 pi by 3. So you can get the expanded version of the signal and shift it by 2 pi. Otherwise, you can separate this omega by 3 minus 2 pi by 3. First you have to shift by 2 pi by 3 and then you need to expand the signal. So I have the expanded version of the signal, so I'll go by the first way. I'll get the expanded version and shift it by minus 2 pi. Okay. So when this signal is going to be shifted by 2 pi, so this is 2 pi here at this point. So we can start from pi to this point 3 pi. So this is 2 pi and this is pi, this is 0. Now this 6 pi is going to be at 8 pi. I'm not drawing this. Now here it was at minus 6 pi. This will shift by a factor of 2 pi on this side. So it will go to minus 4 pi. So it will start from minus 5 pi to 4 pi and just draw like this. Okay. Now lastly we'll draw this. This is 1 by 3 x of e raised to j omega minus 4 pi by 3. Okay, now this original spectrum will be shifted by 4 pi or this one by 2 pi. So let us shift this by 2 pi. So that will be so easy for us. So this 2 pi will go to 4 pi. Now this point is 4 pi and this 4 pi. So I'm drawing it from 3 pi to 5 pi. Drawing the references always help us. Now this is from minus 3 pi to 5 pi. Now again the image which was as 6 pi, it is shifted to 4 pi. We'll shift it by again to factor of 2 pi, or directly we can shift this minus 6 pi to plus 4 pi. Minus 6 plus 4, it will come to minus 2 pi. Minus 2 pi like this. So it will start from minus 3 pi. So this point is minus 3 pi. From this point to minus pi. So it is again a compressed version. So okay. So now let us add these three together. So I am making this first to y of I I'm saying this is y of e raised to j omega after adding this 2. So this is one thing which we are going to add with this and this. So final result I'm drawing in this figure only. Okay. So let us say this image is having center at 2 pi. So let us draw this part here. So this is minus 4 pi. So let us draw it here. So it is shifted to this. So I've added this 2 now. Now next part I'll add this and this to this. So it is centered at minus 2 pi, starting from minus 3 pi to pi. Let us draw this. So it is going to be like this. It is centered at 4 pi. So I am having this plus 3 pi to 5 pi. So this is the spectrum. So this is the whole spectrum y of e raised to j omega final spectrum, which is the sum of all these three. And we can observe that the spectrum is a expanded version of the original spectrum. So you can see here it was pi by 3. So it is coming at pi as the downsampling factor is 3. Okay. So we can see that if this frequency is something else than this pi by 3, then we can observe some gaps if it is less than, and if it is more than this, some kind of mixing will happen here. Okay. So now there is a condition that this frequency is pi by 3, downsampling factor is 3. That's why no mixing is happening. So in downsampling we can observe this expansion in the images, and we will see in the next lecture what effects are observed if this frequency is some different, if the downsampling factor is some different, what relation needs to be maintained in this frequency and downsampling factor, because the spectrum is expanding itself. Okay. So this is just downsampling where the expansion occurs. If we want to, in the case which I'm trying to discuss is a case where aliasing happens in the downsampled version of the spectrum. So we want to remove that aliasing effect, we need to use a low pass filter. Where to use that low pass filter? What is this called? This is called decimation. So what is that decimation process? That we'll see in the next lecture. Thank you so much.